Well, hello everyone. Thank you all for attending this talk called Hackuracy, Boosting AST Accuracy through Hacking. First, I'm going to present myself. I am Andres Roldan. I am a VP of Hacking of Fluid Attacks, a company in Colombia dedicated to continuous hacking services. I'm also part of the GIAC advisory board and have a number of offensive security certifications. These are my social media handles. If you need to speak something about security or something else about this talk, I love talking about these topics, really. Okay, the agenda we are going to see in this presentation basically starts by defining the problems that we wanted to solve during an experiment we've been performing for 10 months now. Then I'm going to give some context about the problems here, described here. Then I'll speak about the experiment we conducted in order to solve those problems that I'm going to present you. Then we will see the results of the experiment. Then we will see some analytics, some metrics about the experiment and how those metrics can be used to take decisions or to choose tools to perform hacking or automatic check vulnerabilities on systems. And finally, we will see the conclusions of the experiment. First, we are going to define the problems that we wanted to solve with this experiment. Currently, you know that most companies around the world are hiring hacking or pen testing services or buying automated tools to check the security of their applications, their systems, their infrastructures, and so on. So basically, hacking or pen testing or anything, as you may call it, is used to determine how secure is a system, how secure is an application. So basically, hacking is being used currently as a measurement tool, and we must see hacking as a measurement tool. A measurement tool, yeah, it makes sense because, again, hacking is the main purpose of hacking or pen testing or anything like that is to measure how secure or how insecure is an application or a system. And if it's a measurement tool, we need to establish how accurate is it. This is the first problem we are going to solve in this presentation. And the second problem is related to hacking itself. Hacking is a tool or a service or something that we use to measure risk exposure on a system or application or something like that. But we know that all the vulnerabilities on a system are completely different. Yeah? The severity of the vulnerabilities are very different, and we need to know that in order to know what is really my risk exposure on my system or application. So, for example, I like doing analogies with this kind of stuff for making it a little more easier to understand. So, for example, if I have 40 benign moles in my body, what should be my risk exposure to my life? I don't know, maybe a little. There are moles, but they are not aligned. So my risk, the risk of my life is not that much. But what if I only have one malignant mole in my body, one melanoma? This really is a real risk to my life. So really, the vulnerabilities itself are not the same, and you can't compare vulnerabilities based on the number, okay? 39 or 100 benign moles in my body means a little, but one single mole that is with melanoma has a lot of risk to my life. You can't compare vulnerabilities based on the number. So if we say that hacking is a measurement tool, we must first determine what makes hacking accurate. And the two things that make hacking accurate first is that hacking should report everything that's true. Okay, so if I have 100 vulnerabilities on a system, hacking or pen testing or the tool that I'm using should be able to detect all the vulnerabilities or at least most of them. And hacking should not tell lies in order to be accurate, okay? So for example, again with the mole example, if I know I have 40 moles in my body and the medical report says that I have 50 moles, there are at least 10 lies in this medical report. So basically when a tool like hacking is accurate, should report everything that is true, but don't tell lies. This is commonly known in our industry as false positives. And the other thing to have into account to check or to say that hacking is accurate is that all the true vulnerabilities in the system are being reported. That means that there are no omissions in the report, and there are no things that were left behind in the report. That is what is called omissions. So for example, again, in the mole example, if I know I have 40 moles and the medical report only tell me that I have 35, there is at least 5 omissions in the report. So hacking is accurate if these two things are met. Regarding the risk exposure, which is the second problem, again, hacking is meant to try to tell the companies or the product owner how exposed is the system, how exposed is the application to the real risks. Other thing that hacking tries to solve is how is the exposure over time? What is my risk exposure today? How is it compared to yesterday's exposure? How is it compared to the exposure 1 year ago? And this is something that hacking should provide as a measurement tool. Also, how is the remediation I'm performing over the vulnerabilities that are reported to me, impacting the risk exposure, the overall risk exposure. If for example, I have the 40 moles and I remove 39 of them, but I didn't remove the malignant one, how is the effectiveness of that remediation that I'm performing, removing my moles, knowing that the real risk is still on my body? So this is something that we should answer here in this presentation. Again, not all vulnerabilities are the same, not all moles have the same risks, not all the things have the same weight, so we can't make decisions or risk exposure based on the number of vulnerabilities. This is really a bad practice. But if it's not based on number of vulnerabilities, how should we measure? What should we measure, really? Should we measure vulnerabilities by range of criticality or severity? For example, how many critical vulnerabilities do I have, or how many high vulnerabilities do I have, according to CVSS, for example? In order to answer the second problem first, I'm going to give you some context about this. You know that CVSS is the most common use standard for scoring vulnerabilities in our industry. Basically, this is a framework which provides an objective severity to vulnerabilities according to this impact. It also provides a way to prioritize and to manage the vulnerabilities according to this score. And one common way that companies and people use CVSS is that they use that score for comparing vulnerabilities. But that comparison has two downsides for us. The first is that again, not all vulnerabilities has the same severity. And you can't say, for example, that 2 vulnerabilities of severity 5 have the same weight that 1 vulnerability of severity 10. You can't do that. That's something that you can't do. Because if you, as you know, a vulnerability of severity 10 is a very high risk for your application, for your system. But 2 vulnerabilities of severity 5 are not very, very severe, and you can add them up. So this is a common mistake, that comparing vulnerabilities according to their severity. And the other disadvantage of the CVSS used commonly in the industry is that CVSS provides 4 ranges for tagging vulnerabilities. So, for example, the critical range are vulnerabilities with score higher than 9. So I don't think, and I don't believe that the vulnerability with a score 9.9 is only 10% more severe than a severity 9. It doesn't make sense. And for example, again, the critical range starts with vulnerabilities starting from 9. But if I'm tasked or I asked to solve the critical vulnerabilities first, why should I first remediate, or why should I remediate a vulnerability with severity 9, but not a vulnerability with severity 8.9? I mean, why is that range created in that way? I think it's something arbitrary here. So this is another disadvantage of CVSS, which is commonly used in this industry. Again, not all the vulnerabilities have the same weight. You can't compare vulnerabilities based on their score, because in this case, for example, 10 vulnerabilities of severity 1 are not the same than 1 just single vulnerability with severity 10. They are different things. You can do that. Our solution is something that we call CVSS-F, F for fluid attacks, in which we adjusted the CVSS score and use it to reflect the exponential nature of risk. You know, the risk is exponential, not linear. And with CVSS-F, we do that, basically making the range of scores a lot more broad. So vulnerabilities which are very rare but very critical will have a real high score using CVSS-F. And vulnerabilities that are a lot common, that we commonly see in all the reports, are having very low values with this metric. CVSS-F basically, again, uses CVSS base score as an exponent to reflect the exponential risk exposure of the vulnerabilities. It provides some really nice features. For example, you can do a clear equivalence comparison between vulnerabilities. You can also prioritize the remediation of the vulnerabilities, but the thing that I love the most is that you can aggregate the values here. You can add the values here. For example, if you have a vulnerability with CVSS severity 10, you can calculate the CVSS-F, and you can add the risk exposure with the rest of the vulnerabilities of the system. You can aggregate the values here. So you can know what is the real risk exposure of your application with the vulnerabilities that are being reported by any tool or any hacking service. The formula we propose for CVSS-F is basically the one here depicted below, where CVSS-F is P, which is a proportionality, saying that how many vulnerabilities are this is really a business variable. You can say whatever do you want here. And you can use P, for example, to tell how many vulnerabilities of severity 9 are equivalent to 1 vulnerability of severity 10. In our case, we chose to use 4 as the P value here. So for us, 4 vulnerabilities of severity 9 are equivalent to 1 vulnerability of severity 10. And the range is basically the range of the values of CVSSF. In this table, you can see how is CVSSF performs against CVSSS. So, for example, in this part, we can see that a single vulnerability with severity 4, some people using the common standard should say that is equivalent to 2 vulnerabilities of severity 2, but we already say that is not possible. So using CVSSF, this is column, we can state that a vulnerability with severity 4 is equivalent to 16 vulnerabilities of severity 2, or 64 vulnerabilities of severity 1. But if you see in the bottom of the table, we can say that a single vulnerability of severity 10 is equivalent to more than 262,000 vulnerabilities of severity 1. This really depicts the exponential ranges from the real risk exposure of the applications and solves some of the disadvantage or downsides that CVSS alone provides. So one of the more important things that I like the most about CVSSF is that you can aggregate the risk exposure and you can make a comparison over time. Here in this graph, for example, some of our customers that are using CVSSF as a metric can have a way to determine what is the risk exposure, how is the risk exposure changing over time for their application, basically. And they can know if the remediation process that they are doing in the development side are doing a real impact on the risk exposure of their application. So this is a very good way to really understand or to view what is the real risk exposure of applications or system based on the vulnerabilities found on their systems using CVSSF. Okay, we solved the second problem first. We are going to solve the first problem then. And the first problem was to check how hacking can be used as a measurement tool. For this experiment, we basically tried to answer a question about how the current tools in the market, automated scanners in the market that provides ways to find vulnerabilities on systems stacked against manual pen testing with expert ethical hackers. That was the experiment we were trying to make. And this experiment was not about comparing tools. We just wanted to check how the tools as a whole compare with manual pen testing with expert ethical hacking pen testing. This experiment is currently being conducted. We are 10 months now of the experiment, and it's ongoing, and is being done by our research team. And the results for this experiment are for a single application, which means that there are specific constraints. The scope is limited. For example, the language of the application being scanned, the architecture, and obviously the scanner capabilities. For the target application, we chose to scan a vulnerable by default application, which was modern, which has a model view controller architecture. It's a single-page application and use a RESTful API, and is realistic and is built on Node.js. That was the application we chose for this experiment. Here in the table, you can see the languages used in this application. The next step in this experiment was to determine the universe of vulnerabilities. So we asked one of the senior hackers of our team to perform a verification using all the tools available for him, manual pen testing, automated tools, and his expertise to determine what was the universe of the vulnerabilities of this application. He, in the time given, he was able to find 1,201 vulnerabilities in 105 categories, the CWE, and a total, the risk exposure of 499 of CBSSF. This is the total risk exposure of this application based on the vulnerabilities found by this hacker. So based on this universe of vulnerabilities, he was able to find most of the vulnerabilities in the code. He performed source code review. He used SAST tools to check what was the vulnerabilities on this application. He found several vulnerabilities in the backend and some others in the dependencies of the application. Regarding the environment of the vulnerabilities, this is very important because 73.2% of all the vulnerabilities found were require authentication to be found. This is important because some of the tools we used to check to perform this experiment didn't have the ability to perform logging on an application doing the dynamic application security testing. So more than 73% of the vulnerabilities were present only after authentication, which in terms of risk exposure is almost 90% of all the risk exposure of the application. This is important to understand. Here is the table of the tools used. Obviously, they are hidden because, again, the main goal of this experiment was not to compare tools, but to compare all the tools against manual pen testing. So manual pen testing is clearly stated here. There is a best tool here that basically outperformed the others. So we will see the results of comparison between manual pen testing and best tools mostly in the rest of the presentation. To understand the results of this experiment, we first need to understand a little of measurement theory. In measurement theory, specifically in hacking, we have four terms which are true positives, false positives, true negatives, and false negatives. A tool that, as an automatic tool or hacking or pen testing that uses that any company use, basically will give you at least three of these. That is true positives, which are vulnerabilities which are confirmed to be existent on the application. Some of the tools that we use on the market have a lot of false positives too, which is something we should take into account. And the false negatives are the vulnerabilities that were not detected by the tool, but are really existing on the application. A good tool or a good service should be able to be reflected like this, should be able to shift a little to the left in the graph, trying to find the most vulnerabilities existing in the target, avoiding as much as possible the false positives, and hopefully not leaving behind some false negatives here. With that theory in mind, this is the result of the experiment. Basically, as you can see here, there are several columns that states, for example, the true positives found by the manual pen testing. In this stage, we selected another team from our company that performed manual pen testing of this application, different from the first hacker that stated the universal vulnerabilities, so we can have a real understanding of what is going on here with manual pen testing. So with manual pen testing, we are able to determine 872 true positives. There are some false negatives that were not detected by this service. This is a real good number, 0 false positives, because all of the vulnerabilities reported were verified. And this is a number that is really important. If you remember, I will going back a little. The risk exposure detected by the first hacker was 461,000 of CVSS-F. If we see here, manual pen testing or the ethical hackers were able to detect 420,000 of that risk exposure. That was really high in the detection of risk exposure. But the best tool, as you can see here, the second line, only detected less than 10% of the risk exposure detected by manual pen testing. And the false negatives, basically what the best tool couldn't see, couldn't detect, is basically the same amount of risk exposure that was detected using manual pen testing. So, and two columns here, precision and recall, are basically detected, are calculated, and I'm going to talk about that a little. This is the rest of the table. And we are going to see some analytics of these results. For hacking or for any measurement tool, there are different models that can be used to check or to say that the tool is accurate. We choose to use the F-score, which is basically a model that predicts how good is a tool, predicting the true instances or true vulnerabilities, in this case of hacking, in a system. So F-score uses two variables. The first one is precision. Precision is basically a ratio or a proportion of the true positives detected by the tool by hacking over the sum of the true positives and false positives. That means that the precision is punished if the number of false positives is high. So the precision gives basically a score of how many false positives were detected on the experiment. And the recall is a metric that basically is a proportion or a ratio of the positive things that were detected by the tool over the all true instances that were present on the all vulnerabilities that were on the application. Basically, the recall punished the false negatives or the omissions of the tool. So those variables are used in this formula to obtain the F-beta score. The most common subindex used in the F-beta score is the F1 score, which gives the same weight to the balance, the same weight to precision and recall, and balance those variables. You can read the results of F1 score using basically this thing below. If a F1 score gives a number above 80%, we are having a really good tool for measurement because it was able to predict at least 80% of the true instances of vulnerabilities in the system. The precision was high, which means that the false positives were low, and the recall, again, is high because it didn't have omissions on detecting the real vulnerabilities on the system. And again, F1 is a balance with precision and recall. Scores below 50% are basically bad scores because it means that the tool being used, the performance of the tool was worse than random guessing. So we will see that some of the tools, most of the tools have scores below 50%, which is really, really insightful for this experiment. We also calculated two other F scores, which is F0.5 score, which gives less weight to recall and more weight to precision. So it will punish more when the precision is lower. And the F2 score basically gives more weight to recall, basically punishing when the recall is low. The F2 score will be low too. Using those F scores, we can see the results again of the experiment. First, you can see the first line with manual pen testing, which had a F1 score of 84%, which is, again, is a really good number, as we see earlier, because this technique or this service was able to detect 84% of the all instances or the true instances of vulnerabilities of the application. According to the F0.5 score, the score was 93%, which also very, very good, which means that the amount of false positives were low, and this score should be used for developers to choose a tool, for example, because in the development process and the remediation process, commonly the severity of the vulnerability is not important to solve the problem. Commonly, the time to resolve a vulnerability is not dependent of the severity. So as a developer, I like a tool that tells me the less lies possible. So I need to use F0.5 score to choose a tool which gives me little lies. And the F2 score, basically, we should see F2 score based on the risk exposure it was able to detect. In the last column, you can see that with manual pen testing, the F2 score was 92%, which means that it was very good detecting almost all the true instances of the vulnerabilities on the system, which was really high on risk exposure here. And you can see here that the best tool amongst all the tools that we checked in this experiment only was able to detect 10% of the risk exposure. So really, it missed almost more than seven times of the risk exposure that manual pen testing was able to detect. This is a graph in which the F1 score can be seen more clearly. Again, the manual pen testing F1 score was 84%, which was really, really, really good. But the best tool was only 36%. Again, as we can state earlier, a tool that that have scores below 50% are basically worse than random guessing. So this is a very, very important thing to notice. But regarding the severity or the risk exposure of the application, the F score of the manual pen testing was really high because it was 95%, while the best tools of all of the tools we checked was only able to obtain a 16% of I1 score regarding severity detected. This graph is really cool because you can see the three F variables here in function. Basically, the x-axis is showing the F0.5 score, and the y-axis is showing the F severity score here, and the diameter of the circle is the F1 score. So the best tools should be near this part of the graph, and as you can see here, manual pen testing again outperformed by a lot the rest of the tools that are in this graph here. This graph again shows the F0.5 score and the F2 score in the experiment. And this graph again shows that the risk exposure that was detected by manual pen testing was a lot compared to the best tool that was only able to detect only a portion of the risk exposure of this application. The execution time is the really downside to manual pen testing. You know that, because automated tools can run in minutes and seconds, basically, but manual pen testing should commonly take days to give you a result, but it's a trade-off that you should be aware of during hiring a hacking or pen testing service or automated tool. Okay, so to conclude this presentation, we see that manual intervention is still necessary to achieve high accuracy with hacking. 74.8% of the vulnerabilities were only detected by manual pen testing. No tool were able to detect 74% of the vulnerabilities of the application. The best automated tool was only 36.9% accurate with a F1 score in finding vulnerabilities. And the best automated tool was only capable of discovering 8.8% of the risk exposure, which is really, really low, while manual pen testing was able to detect 91.9% of the risk exposure of the application. Again, this, going back to the first conclusion, manual pen testing, expert hacking, expert review of the target is still necessary to have accuracy when detecting vulnerabilities in a system. Thank you very much for attending this talk. I hope you liked it. These, again, are my handles for social media, so you can follow me. We can talk about this talk and other topics that you might want. And I don't know if you have some questions.
Yeah, I have a question. Did you, in testing various different tools, just out of curiosity, did you include any... Hi, okay, there. In your testing of various different tools, just out of curiosity, did you include any like AI-related bots that could go in and do some of that automated testing as well?
Yeah, it's a very good question. We didn't have that variable in mind when we tried to choose the tools that we are going to use for this experiment. But I made the same question to my team yesterday because I didn't know that. And again, this experiment is ongoing. Maybe in the future we can talk about the results with AI tools used in this experiment.
So I have a question regarding the benchmark application that you used. Okay, that's good. So I have a question about benchmark applications that you used, or one application.
Mm-hmm.
Is it open source? That's one. And the other being, so how did you determine the baseline? So the false negatives that the penetration tester wasn't able to find, mm-hmm. How did you know it was a false positive, it was a false negative if you didn't manage to find it in pen testing?
Yeah, of course. Okay, the application chosen was one of the most, I can tell the name for some reasons, but basically it's a very common vulnerable by default application. Is open source, is available on internet. There is a lot of vulnerable by default applications on the market, and we chose one that was modern, that was realistic, and had a modern architecture. Regarding the other part of the question, the first thing in the experiment was to assign a senior hacker to determine the universe of the vulnerabilities. He was doing manual pen testing by himself a lot of time, maybe 2 months, I think, and he was able to detect, again, over 1,000 vulnerabilities. That was the baseline we used to determine what was the true positives and false negatives ratio.
I see, okay. And what was the amount of time that you invested in the manual pen testing after determining this baseline?
49.
Compared to like the automated tools?
Yeah, it was 49 days. 49 days. That's the really downside of the manual pen testing. You need a lot of time to obtain the results, but it's basically, again, a trade-off of accuracy that you need to go.
Hi. How did you come up with the idea of using an exponential for the relationship between CVSS and CVSF?
Yeah, I need to admit that it was not my idea. It was of of our data scientists that come up with this idea. And basically, we come up with this because one of the most common questions that we are being asked during our time of fluid attacks is how do you compare the risk exposure of applications? And we again see that comparing based on CVSS is not a way to go. So our data analyst or data scientist came up with this idea of using CVSS as an exponent to make it go to a broad ranges of values using CVSSF. Okay, so thank you very much again, and cheers.